why would we look at biology? Well, we're coming from a neuroscience perspective, and we like this idea of reverse and forward engineering the system. So there's a really powerful face recognition system within all of your heads. And basically, from the moment you're born, it's been shown that babies start looking at faces, they're attentive to faces, they look at them more than other things. By age 1, pretty much face recognition experts, they have invested in all of the systems available. And faces are deeply ingrained in biology, so you see faces even when they're not there. And importantly for what we're going to talk about today, face recognition in biological systems is incredibly fast and accurate. So if you just look at the screen, some images are going to flash up. And even though those were up for a very short period of time, everyone will know what those spaces. And furthermore, humans with enough training can do incredibly fine face recognition problems. For instance, something like our twins, even though it's a highly cluttered background, very complex. So I'm not saying that this is the only way to go about doing face recognition, but I guess I would just say, ignore biology as your own peril. This is the one example of a system that really works. So we're taking the approach of studying. So how is biology organized? So we have an image like this image of John Havard here. Basically what happens is photons from that image enter into the eye. They're transduced by the retina, which is a photosensitive tissue on the back of the eye. From there, it travels on the optic nerve to the brain. Now, the brain is massively parallel computer, and each is made up of hundreds of millions of neurons. Each one's like a little tiny computer, takes in inputs and transforms them into outputs. Now, we can take clues from how the brain is organized and try to think about how we can organize our artificial system. So in particular, when information comes into the back of the brain, the occipital lobe, the information goes to the back of the brain and then it's successively transformed in a hierarchy of visual areas. So the first area is called B1, followed by B2, followed by B4, and then there's this area called TE at the end. And if you do recordings with microelectrodes in these areas, you find that if you predict for a moment that they're neurons and treat them as a feature vector, responses to these neurons, they're pretty much the features you want to have. You can put a classifier on those features, and you can do incredibly hard object recognition based on gene tasks. So the goal then, for what we're doing, is to try and take this biological system and mimic the architecture in an artificial system. And where the natural system has a series of neurons that are doing the computation, the artificial system has a series of functions that we're going to define. Now this has been going on for a very long time, but there's a problem. So those functions in each of these neurons, in each of these layers, have parameters associated with them. And even if we have the right set of ideas, we don't always know how to arrange those parameters. So one set of parameters we might reasonably try will give us one set of qualitative behavior. But if we try a different set of parameters, we're going to get a different behavior. And then likewise, another set of parameters and another behavior. And at some level, we also don't know how to arrange things like even the size of these hierarchical layers. So maybe you might want to have a big layer 2 and a smaller layer 2. So these are questions that are sort of over and above the sort of computational insights we've been able to derive from neuroscience, but we have this problem that there's lots of parameters, lots of free parameters that we have to just sort of guess at. So, in fact, even if we have the right idea, we have the wrong model, and we could be sort of misled about performance, because there's really this huge constellation of possible models that fit that idea. So we can sort of drive meta-inspiration from biology. So we're driving inspiration from biology on building models, and we can drive inspiration from biologists on how to study them. So if a biologist wants to study an organism like bacterium, what they'll do is they'll plate them out onto these petri dishes. And the basic way this works is the scientists will plate out bacteria. Each one of these contains slightly different bacteria just by random chance. And then if you want to find ones that have a particular property like resistance to a particular drug, you just apply the challenge, and then in parallel, all of these bacteria that are not resistant to the drug are killed, and then you're left with the one that has the property you're interested in. And then at your leisure, you can study those. So you might look at these and try to figure out why they have the resistance, or you might just replay them and play the game again and enrich the population. So to take that idea to our machine vision problem, we can take this huge diversity of biologically inspired models and we can apply a challenge. And in this case, it's going to be a face recognition test, a traditional evaluation problem. And we're going to apply that in parallel to a huge number of models. And then we're going to find the ones that do best, and then we're going to study how they work. So to do this, that's a huge amount of computation. We do that with GPUs, and crazy machines with lots of GPUs and many fans. Not enough time to talk about that. If you're interested in that, please find us afterwards. I'm happy to talk about that. But let's move on to what the actual models are and get a little more detail to motivate. So this is the basic structure of those models I was showing you in a sort of cartoon form, slightly less cartoon form now. Basically, we're going to work on grayscale inputs now, so just for the sake of simplicity, we're actually going to work on color ball. So you might take a face image like your arena, and then it's going to go through a cascade of processing operations. So there's, in each layer, we have basically a convolutional type operation. It has to be a correlation, that doesn't really matter. There's going to be some non-linear static nonlinearities, like a threshold saturation, some pooling operation, downsample the image, and then, importantly, some local normalization. So these are all operations that we learned are likely to be important from biological experiments. And then this structure is repeated in multiple layers, and then we just take the output of this and put it into a classifier, so which is a linear SVM. So really the goal is to take this image and re-represent it into something that's good for doing whatever task you want to do. In this case, task. So just to walk through, this is just some equations from the paper, just to orient in case you're that. Basically, the operation is a filtering operation. This is like the correlation I was telling you about. There's an activation, so there's threshold saturation, downsampling, potentially allowing something like a max operator, and then this normalization. It basically takes a region of the sort of virtual cortex and then normalizes one of those vectors. And the details you can find in the paper, it's really not time to get into those right here. And this is a little bit more of an intuitive sort of picture of what this looks like. So basically, it puts them in here, and then we have a series of layers, and then there's sort of a convolutional scanning, and then that flows up at the top where we use it to read out the classifier. Now, just to zoom in, this is the important takeaway point. Everywhere I've drawn something in red is a parameter that we don't have biological constraint for. We don't have even computational constraint for yet. So we don't. We have the right model, but if we get these parameters wrong, maybe we'll miss the basic. So those are the properties that we're going to then screen over. But to do screening first, though, we have to know what we're going to screen. What's our challenge? And for this, we surveyed the face recognition literature. We're coming sort of from outside of the face recognition field. And the first thing we noticed is that a lot of the standard test sets feel like they mostly install. So we saw some 99% numbers, not a lot of dynamic range. So we wanted to go somewhere where this is still very hard. And luckily, right around the time we're getting started on this, Eric Leonard Miller's group in UMass created this basis in the wild set. And just to give you a flavor of what this looks like, if you're not familiar with it, here's just a sampling of the faces that include people with the same name as me. And you can see that there's lots of sort of unconstrained examples of faces. These are just taken off the internet. And you can see that the backgrounds are very variable, the poses vary. This is why they call it in the wild. It's meant to include the full range of variations you might find in the real world. So this is how the challenge works. So we get two images, in this case it's the same person, and it's verification now, so you have to say the same. So if we have two images that aren't the same person, we have to say not the same. And then that's a bit of a complication for the model I showed you, which is a sort of generic feature vector model. So we can't just feed the raw feature vectors that come through this approach into a linear SVM. We have to first take that feature vector, and then we have a way to process pairs. So basically what we did is we created a set of comparison functions. So basically we take the image 1, put it through a feature vector, image 2, put it through a feature vector, and then we compute a couple of different comparison functions. Basically just feature vector element-wise map, so that we get one thing, we can then train the SVM on same and not same. And for the sake of simplicity, since we didn't have any physical way of saying which ones we were better, we just trained all 4 SVMs and just together. So this is how the screening works. So I told you we're going to have a huge range of possible models. So here's a histogram of performance on the x-axis and the number of models on the y-axis. So this is about 7,000 models that we ran. They're relatively large models. We ran a lot of them. And then what we're going to do is we're going to take the best ones and we're skim off the top, and then we're going to study these guys further. So these are the top 5 models. And the way that LFW is organized is a view 1 set, which is meant for model selection. And that's what we use for model selection. And then there's a view 2 set that we can then evaluate on afterwards. So for what follows, I'm going to actually tell you about 3 different classes of model. One is something that I didn't tell you about before, which is called P1-like, which is a very simple 1-layer model with has constrained filters that are happen to be divorced. There's reasons for this, but that doesn't matter right now. And then I'm also going to tell you about 2-layer models and 3-layer models. So we screen the best ones, we get the 5 best 3-layer models, 5 best 2-layer models, and then we can compare them on this LW2 task. So here's the performance of a variety of approaches that are likely to be very familiar to everyone in the audience. So eigenfaces, SIFT, Hmax, C1, this is a biologically inspired model, and then LVP and LVP variance. So you can see that this is a hard task still. We sort of haven't solved it at this point. And the performance is sort of around 69% or so. If you take our V1 model, which is again a 1-layer model, we can see that this approach maybe is already looking a little bit attractive. So we're a nice solid margin above, and then we start looking at these more complex multi-layer models, the HDL2s, the 2-layer model around 81%, and the best 3-layer models around 84%. So we're getting very large gains relative to the traditional tools that are used in these fields. Now, these aren't actually the state of the art, and one of the nice things about AFW is there's a lot of smart people competing on these challenges. So here are some of the state-of-the-art results, and these are coming in all the time. And basically, so this is from a paper by Wolf and company, and this is from Peter Bellmer's group. Basically, when you get up to the high levels of performance, it ends up being a lot of blending. So here is from that paper, LVP plus C1 plus a couple different LVPs and SIFT, blended them all together, and got about 75%. Now remember, our V1, which is our simplest model, is already at 77%. So there's something about the features being strong. It's more than just putting a bunch of weak features together. And then the best number they get out of the paper is LVP plus C1 plus TPLV, 4 LVP plus SIFT, so maybe 1-shot similarity, 2-shot, and then it's like a snowball. So they take everything out of the paper and snowball from one thing, and they get 86%. So, and then this attribute similarity one is sort of a smart idea where you train attribute classifiers and use that to do the verification test. To get into on the blending game and these things to blend, we generate thousands of models, so it's not hard to model. No shortage of things to blend. So this is just a table out of the paper. We have multiple 2-layer models and 3-layer models to play with. In addition, we introduced this idea of crops, such multiple different crops of the same image that we scaled, so just resampling the image, just throwing those in the pot. Also, we have blends of different stuff. And then when we play these games, the top 5 L3s are achieving a state-of-the-art number by themselves. So we just put the best 5 L3s together. And then if you take the V1 and the best L2 and the best L3s, blend them together, we get a similar number. And then if we do an a priori weighted blend, so basically we just sort of decided that we're going to weight the L3s more than the L2s more than the V1, and we just do a weighted blend, then we get this number. This is the current state-of-the-art number for the moment. These can change on this challenge. So we have a lot of material to work with. So basically we used a little bit of blending until we got tired of blending. We got a lot more to blend, but I don't know if we need to blend. I mean, I don't know if we really play that game, but anyway, there's a lot of legs in this approach, we think. So just to conclude, powerful features make a big difference. And this large-scale approach enables finding sort of the needle in the haystack, these really powerful features that can use in a wide variety of approaches. And the other point is biologically inspired features oftentimes have a bad rap, and I'm not sure what that is, but it's a really rich source of computational ideas for building these kinds of features. So with that, just going to skip that and acknowledge people contributors, particularly people at Pinto, who's in the front there, some of our collaborators at MIT or Harvard, and all of our funders. And I'd also like to thank you for your attention.
Okay, quick question. How task specific is your specific hierarchy? So if I were to put in like the standard, FR2C database or even object recognition databases, how specific are the functions and the layers geared towards the database that you tested?
So I'll actually put in that slide that I skipped over. So the answer is not at all, and apparently that's a problem. So this this was a review we got of an earlier draft of this. He says, it was a reject. He said, but I failed to see, and this is a major disappointment of this paper, is how the proposed processing representation is any way peculiar to base processing. In fact, from the paper, the proposed representation be applied to any image representation recognition task, not just faces. Reject. What? So we're actually coming from output, right? So we're a little bit of invaders. We can pretty much put anything. I mean, the biggest hurdle was that comparison function thing, because the verification test doesn't fit as nicely into that box. Now, the face recognition program challenge, we haven't played with it yet. Partly, it's just harder to get, and we're sort of not in the game. So we're going to get it and try it out. LW just now on the internet, so that obviously starts there. We've also been playing with images from Facebook. These really large sets. And we take the exact same models and see if they generalize to each other problem. And what we find, so here we're doing, this is a bit off topic, but we're taking a 100-way face identification. These are real images of real people's Facebook accounts. And then this is the same best L3 that I was showing the data from before, and we can get sort of, 80+% accuracy on a 100-way face recognition task. So this is not only generalization of the approach, this is generalization of the exact same models to a different, even a different paradigm, right? Because we're doing a 100-way classification of so this is 100 class SVM, not comparison. So the bottom line is there's nothing about this that's specific to this test set or even faces or anything like that. The other thing that's interesting about this is, we maintain sort of spatial context. So this is a feature, this is like SIF or any of these features. If you apply across an image, you get basically just an array of feature vectors. So if you wanted to build something on top, using something that was peculiar to faces, that would be great. That's sort of what we came. Actually, I forgot to show this slide. If you wanted, we don't have the code available yet, but we're planning to make something available. We're not quite sure what. We need to work through that. But if you're interested, there's a place where you can sign up. Basically, you can buy
Actually, I would like to ask, what is the major difference between your work and the work of Poggi, published in PAM in 2007, in object recognition with cortex-like mechanisms?
Yeah, so Tommy's model, it's similar in spirit, for sure. So I don't actually have the numbers for the full model. So basically, Tommy's model is like one special case of this larger class that we search.
So it's a generalization.
It's sort of an aggressive generalization. The other way we treat this too is like this is sort of like a laboratory for us to try new things. So the HMAX model has very particular sort of bits and bobs to it, and those are relatively static. We're treating this more like a sort of boiling cauldron that we're throwing stuff into and letting it heat and finding the interesting parts. For instance, though, a lot of the things that are sort of cited as being important parts of HMAX don't actually emerge as being things that are required for getting best performance. But it's good. It's part of the discussion. So if HMAX were sort of like the one and only answer, it's in there. It could emerge, but this gives you a framework for sort of being doing about how it works. Great, thanks.
Very nice presentation. I just had a quick question. So, I mean, one of the premises of your talk, it seemed that you had like biological inspiration behind everything. So the system that you're going to build has a lot of capacity, but as you said, like you've got lots of different fine-tuning parameters that you need to find. So the one thing I'm a bit puzzled about is, so what's the underlying understanding of why this works? So why, I mean, like, so we see these things in biology, and okay, it works well, but there's a lot of examples in biology where we switch them back the other way, they don't work. Like if I was to design an eye, I've got a blind spot, I would never design a camera that way. So just blindly applying biology, flipping it back the other way, and just finding numbers. I'm just wondering, where's the understanding? Why does it work? Right? And just sort of, great, we've got great numbers, we see this in biology.
Sure.
So I'm just sort of wondering, are you guys dealing with that sort of question too? Or?
Absolutely. So the eye is sort of an interesting example because, yeah, you wouldn't want to look at the, it definitely argues against sort of rote mimicry. I mean, you don't just be sort of slavish to biomimetic for the sake of being biomimetic. And there are groups that really care about getting all the ion channels just right and simulated and all that stuff. Yeah, that was a great example though, because while the blind spot is phenomenal, quantum efficiency of a photoreceptor is absurd. You detect a single photon. Camera developers could do well to try and study the eye.
We could throw stones back and forth. There's lots of examples where voltage is great, but there's other examples where perhaps it's
Well,
and so I'm wondering, like, kind of like, just blindly saying we motivate by biology, that kind of perhaps, I don't know, I'm just sort of...
Sure, no, I agree with your point. I think it's less a discussion of, is biology good or is biology bad? But the interesting part is there are parts that are phenomenal that just aren't important. There are parts that are deeply important. So we have sort of, behind this all, there's sort of a lot of deep theorizing, right, that we do, and that's why we're doing this. What this gives us is a tool to sort of separate the wheat from the chaff, right? So if there are blind spots, that, like parameters are effectively like blind spots, they're in there, they're not going to help, and that'll be completely clear. So right now, this is just a random search, we're just randomly searching around space, but we can also do sort of focused experiments where we say, okay, now we're going to do, blind spot on, blind spot off, and see, okay, Thunderdome, let's have a fight, and see whether it's important or not. And you can sort of take things off the table and do that separately. In terms of the actual reasons why this is useful, I think there's a lot of sense to how hierarchies control dimensionality, so that you're not trying to swallow a super high dimensional problem all at once. If you're building out the structure of actual images is one over F, so it makes sense that you might want to do something similar at multiple scales. So that's a sort of sensible property of these hierarchies. There's a sense in which you can think about what they're doing as modeling the structure of images. There's certainly elements of sparsity, so a lot of the features end up being quite sparse because of nonlinearities, and that sort of makes connections to immersive sensing. So basically, it's a sort of nice sort of tool now that we can take all of these ideas and try and make sense of them and move it forward.
Let me break in and move us towards the break. We start again at 10:30. Let's thank Jamie and